Today we're going to demo the software that comes with the Bachmann Technologies PB7220 series of spectrometers. When the software is installed on your computer, it will put two icons on the desktop, and it will also create program directory under your programs under the Windows Start button. There are two icons that are created, one that will connect you as a shortcut to the data and is labeled data, and the other one which is labeled PB7220 control. So if you double click on that, first thing you'll see is the system communicating with the PB7220. This system has already been run on this computer and the calibration file has already been downloaded. If it is the first time, then it will take about 2 minutes to download the calibration file from the system to the computer, but after being done the first time, should not have to be repeated. So the program looks like this. Let me zoom in on it. It's fairly simple to understand and to operate. You have two tabs on the left. The first tab is for scanning. The second tab is if you want to sit at a specific frequency, and we'll look at that in a minute. But for scanning, you have the start frequency, the stop frequency, and these will be controlled by the limits of the system, so you can never get these wrong. The limits, for instance, on this system, if I try and set 50 gigahertz, this system has a 200 gigahertz lower frequency. Set this one to 2400, it's a 2000 gigahertz upper frequency. The step, or the resolution element, can be as low as 100 megahertz or as great as 5000 megahertz. Typically, we operate at 1 gigahertz or 1000 megahertz. Time constant. The system uses a lock-in amplifier. It modulates the source photomixer and looks for that modulation frequency on the detector. And so you're given a time constant from 10 milliseconds up to 10 seconds. We recommend starting your analysis at 100 milliseconds. This is a good number for the system to operate. If you have very highly transmissive samples, you can go to lower time constants. The time constant sets the dynamic range of the system. The longer that the system integrates on a point, the further down the noise floor it gets. So if we were to change this time constant from 100 milliseconds to 1 second, our noise floor in the power measurement would decrease by a factor of 10. But this would be a 1 second time constant, so that each sample that you take, say 1 gigahertz, so there's 1800 points in this measurement as set up. Each of those points would require a second, and it would take 1800 seconds to complete the measurement, whereas with 100 milliseconds, it's going to take 180 seconds to complete this measurement. Scans. The system does averaging, so you can use averaging to improve signal to noise ratio and also increase the dynamic range. So a time constant of 100 milliseconds, an average of 10 scans, is the same as a single scan and a time constant of 1 second as far as the noise floor is concerned. When it comes to signal to noise ratio, which has to do with noise on the actual signal, the terahertz signal, and artifacts, averaging the scans improves the signal to noise ratio. Long stabilize. When the system is being used in a very high resolution manner and you're taking steps of 100 or 250 megahertz and you want high accuracy, then you can choose long stabilize. That takes and makes the lasers stabilize for a much longer period and therefore start at a much more accurate frequency. Next is the weighted smoothing and the smoothing. Because we do averaging, we also have the ability to do smoothing. What I'm going to do here to illustrate that is we're going to do a really short scan, and we'll use a 2000 megahertz step size, 100 millisecond time constant, and we'll just do a scan up and not back. Actually, no, we'll do a scan up and back. First thing it's going to ask you is if you'd like to take a background for these measurement conditions. What that allows is if you take a background, then it will be subtracted from data that you take after recording that background. For the moment, we're not going to do this. We're just going to say no. We're just going to do some illustrations of how the software works. As the lasers are stabilizing and the system is going to the start frequency, the software indicates that the system's stabilizing and it'll keep flashing red. This would be also a good time to show you some of the other features, like under Tools, if you go to Monitor, then you can sit here and you can monitor what the lasers are doing. If you click on these, you can also find out the photo current for the source photo mixer or the detector. We do not always gather this information because it slows down communication with the computer. Let's go back to the scan, and I'm going to turn off the smoothing. Smoothing by 1. Here we have a couple of different tabs. First tab, smooth power, is also the average power, whereas this is the raw power. No averaging or smoothing occurs on the raw power or the raw voltage. And as you can see, as it scans up, we have a trace in blue. Now that the system is scanning down in frequency, the trace is in red. Go to smooth power. We can see it making the changes here as it does the averaging. Now, as we do smoothing, we can get rid of the effects of the interference pattern. And this is good for looking at very, very broad features. Go to the raw power, we still see the fringe pattern. And the raw voltage, obviously we see the fringe pattern. Well, that should give you some idea as to the power of the software for scanning. Next, we're going to switch to Dwell. Dwell is simply you set the terahertz system to a single frequency and you can measure the power at that frequency. This is good for, obviously, for single frequency measurements where you're expecting a change in the sample over some period. Again, we have the set frequency, the time constant. This is the frequency that is actually running. This is a passively set system. So you set it to 300 gigahertz and it will tell you what the frequency is. Active control forces the system to the 300 gigahertz. This is typically the default. And then as you set up the system, if you want to start recording the data, you click this button. It's not necessary to click it when you hit start, but just when you want to start taking the data. So let's set the system to, say, 800 gigahertz and start the Dwell. Unlike with the scan, the Dwell system does not wait until it is stabilized. You actually get to see it start stabilizing and read what the frequency is. Now, as this yellow indicates it's not stabilized yet, when it gets within about 250 megahertz of the desired frequency, turn green and it will determine that it has stabilized. So here you can see your signal and here you can see the power. Both of these are in power. If you hit the record Dwell data, it will start recording. We'll click that and now it has started recording the data. So when I put my hand in the beam and block it, now we're down at the noise floor. Remove my hand. Now we're back to our original power level and we've stayed right around 800 gigahertz.